Assalamualaikum and good day to Dr. Firdaus. So we are from Group 5, presenting for the subject Foundation Engineering from Section 3. For the company background, Terastra Engineering Sdn Bhd formed in 2018 as an engineering consultancy firm that specializes in foundation and geotechnical engineering services. Terastra Engineering Sdn Bhd also emphasizes the importance of understanding soil properties to ensure that the selected foundation system is safe, stable and suitable for the proposed development. Operating mainly in Kuala Terengganu, the company is experienced in handling soil conditions common to coastal areas. So this is the organization chart for our company. The director is Luqman Hakim. The project manager is Danish Darwin. Project executive is Farshad Yuldina. Project engineer is Catherine Narus. And site manager is Zura Ain. Next, the vision and mission of our company. Vision to become a trusted foundation engineering consultancy company recognized for quality services and professional practices. Mission is to provide safe and reliable foundation solutions, to conduct proper soil investigation for construction projects, to comply with engineering standards and regulation, and lastly is to ensure customer satisfaction through quality work. So for the project location is at Kuala Terengganu in Terengganu Darul Iman. The project aims to provide a suitable foundation system for the proposed bungalow development using site-specific data collected from soil investigation results. This project involves investigating soil profiles, estimating the necessary soil characteristics, and determining a suitable shallow foundation system for the bungalow. The assessment includes determining the bearing capacity and settlement of the proposed foundation to ensure stability and safety.
Assalamualaikum warahmatullahi wabarakatuh. My name is Luqman Hakim bin Luqman, matric number CF 210001. Now I will present about element of consideration to do site investigation works. SI conducted to propose bungalow. Objective to identify subsurface soil conditions for the design of shallow foundations. SI work, which is borehole drilling, standard penetration test, groundwater level measurements, and laboratory testing, which is disturbed and undisturbed sample. For the shallow foundation design, shallow foundation depth must prevent erosion and surface water damage, provide resistance against sliding and overturning. Typical depth from 1.5 to 3.5 meter based on public work department. From below ground level, the function is transfer structural load, distribute load safety. For the key performance criteria, adequate bearing capacity and control settlement. There's 25 mm for the building. For the factor of safety, 2.0 above. Now I will continue about site investigation overview for borehole number 1. Subsurface condition, borehole depth approximately 36.30 meter. Soil profile, upper layer dominated by granular soil, top 1.5 meter, medium dense brown seed sands. Below 1.5 meter, medium dense silty sand with seed and gravels. Soil density increase with depth. For the soil at foundation level, which is the FR 1.5 meter chosen, medium dense silty sand that's area. For the summary of SPT result, borehole number 1, the depth chosen 1.5 until 16.5. Want to use during calculate the design and settlements. SPTM value range within 11 until 21.
The groundwater condition observed during the soil investigation. The water table was recorded between 4.5 and 36.3 meter below ground level. Since our foundation depth is only 1.5 meter, the groundwater lies well below the foundation level. This means its influence on bearing capacity and soil firm is negligible. Therefore, groundwater effect can be safely excluded from our shallow foundation design consideration. Next, we conduct laboratory tests on undisturbed soil sample from Borehole 1. This included density tests and considered undrained threshold tests to determine the soil physical and engineering properties. The bulk density ranged from 2.026 to 2.039 milligram per meter cube, with an average of 2.032 milligram per meter cube. This corresponds to a unit weight of approximately 19.93 kilonewton per meter cube, which we use in our bearing capacity analysis. The threshold test provide effective stress parameters suitable for a long-term foundation design. The soil exhibit an effective cohesion of 9 kPa and a friction angle of 34 degree, indicating medium dense silty and with good shear strength. Bearing capacity consideration. Bearing capacity refers to the maximum pressure that can be applied at the foundation level without causing shear failure. At the BH1, the soil type is a medium density sand with a high friction angle, which suggests general the shear failure as the expected node. Therefore, the Zaghi local shear failure equation is appropriate for the shallow foundation design. We apply the factor of safety of 2.5 and use the following formula for the square footing. So you can see here, there's a formula for bearing capacity consideration. Okay, next, settlement consideration. Settlement behavior is another important design factor. The medium density sand at the BH1 show the low compressibility, meaning settlement value are expected to remain within an acceptable limit for a low to medium risk building respectively. Differential settlement is not expected to govern the design. To estimate elastic settlement, we use the theory of elasticity based on the Hooke law. The formula include the net applied pressure, of elasticity, Poisson ratio, effective foundation weight, and Steinbrenner's factor shape factor. This ensures accurate prediction of the settlement under structural load. So you can see here formula for the settlement consideration.
In this project, we have calculated the foundation analysis. This analysis is crucial for understanding the structural integrity and load-bearing capacity of our proposed foundation design. For Group A, the size foundation is 1.5 meter times 1.5 meters. The load from the column is 36.8 kilonewton. The gross load allowable is 642.8 kilonewton. The settlement is 10 millimeters. For Group A, the foundation size is quite compact and the load is relatively low compared to the allowable gross load. The settlement is also within acceptable limits, indicating a stable design. For Group B, the soil foundation is 1.6, the load is 112 kilonewton, the gross load is 610.3 kilonewton, the settlement is 28.8 millimeters. For the Group B, we see an increasing in size and load. While the gross load allowable is still sufficient, the settlement is slightly higher, suggesting that we need to monitor this more closely. For the Group C, the load has significantly increased. However, our gross load allowable comfortably exceed the applied load. The settlement of 16 millimeters may raise and could require further investigation. For the Group D, it is shown another substantial load increase while remaining below the allowable limit. However, the settlement of 105 millimeters is alarming and warrant detailed analysis or redesign to minimize movement. For the Group E, we are at the upper limit of our design criteria. The load significantly approached the gross allowable load, and the expected settlement of 155.3 mm is quite high.
Okay, so next is I'm gonna explain about the soil improvements. So in soil improvement, it includes four aspects, which is excavation, replacement with granular material, lean concrete blinding, and also moisture control. For aspect in excavation, the consideration is to avoid over excavation and also soil disturbance, which the engineering purpose is to maintain bearing capacity. While for the replacement with granular material aspects, the consideration is to remove of loose and replacement with compacted sand, which the engineering purpose is for suitable for shallow foundation excavation. Then, for lean concrete blinding aspect, the consideration is the thin concrete layer placed at base of excavation, which the engineering purpose is to improve the load distribution and also cleanliness. And lastly is the moisture control. The consideration is the control of soil moisture before compaction, which the engineering purpose is to prevent loss of strength in silty sand. That is all for soil improvement.
This study identified the most suitable foundation system based on the specific site condition. An analysis of bore log data, SPT result, and soil parameters emphasized the significance of a shallow foundation for maintaining structural stability. A pad foundation was determined to be the best method for efficiently addressing the challenges faced by soil layers while ensuring long-lasting durability. Moreover, the study explores soil improvement techniques aimed at increasing the load-bearing capacity of the ground. These methods are vital for optimizing foundation performance under various soil conditions, reducing settlement issues, and enhancing overall safety. In conclusion, this study enhanced the understanding of foundation engineering, underscoring the necessity of site-specific assessment in construction projects. Future research could leverage advanced geotechnical modeling and in situ testing to refine foundation design strategies for similar soil environments.